So let's talk about work, and we'll talk about power, and then we'll go back to our conservation of energy idea. Okay? All right, remember, work. Work is the transfer of energy. Okay? From one object to a new object, from one place to a new place. Okay? That's what work is. All right? Work is accomplished through forces. Okay? Because forces are the agent of change. If there wasn't a thing called a force, or if forces didn't exist, then nothing would change. Everything would stay exactly the same. Okay? So forces are the things that make things change. All right? They're the agent of change. And so let's do this real quick. If we have an object right here, say it has mass. Actually, here, let's do this. Do it another way. All right? Mini textbook. Here we go. Textbook. Kaplan AP Physics, B and C. All right. So if I take this book and case number 1. Did y'all see it?
Yeah. Yes.
What?
Okay, wait a minute. From right now to right now. Okay, did I do work?
You didn't. Yes, you had the book.
No, because there was no displacement.
Oh yeah.
Haha. In my perfect physics world, no. Why not?
No displacement.
Did I change? Did I transfer any energy to it?
No.
No. Did I change its energy in any way? No. Okay, and there was no displacement was another way, okay, that you can figure it out. All right, so, okay, you ready? All right, ready? From now to now. Was there work?
Yes.
Okay. Did I do positive work on the book or negative work on the book? Meaning, did I add energy to the book or take energy away from the book? Add energy. Okay. So what kind of energy did I add? Potential energy. Okay. I had gravitational potential energy. So I did work. When I did that, that took energy away from me and gave it to the book, right? Okay. All right. So, okay, you ready? Okay. Not now yet. Okay. Now.
Yes.
To now.
Yes.
Why not?
Because you're still holding the book. You're moving yourself. You're not moving the book.
Relative to yourself.
Yeah.
All right, so here, let's do it again. Okay, not now, but now to now.
There's no. The
No,
potential
you're
energy is
still
the
moving
same.
your
The
book.
height's the same.
Ooh, so the
gravity's
potential
same,
energy is the
and
same,
velocity's the same.
and is the kinetic energy staying the same?
Yes.
Yeah. So now, was there? Wait a minute. From now until now,
No.
did I do work?
Yes.
What kind of energy did I give it? Kinetic. Okay, wait a minute. Now, how about from? Wait, was that positive or negative work? Positive. Okay. All right. How about from now to now? No? I'm getting tired. Didn't I do work?
No.
That's my fault.
Exercise more.
All right. No work? Why not? I moved it.
You didn't change the energy.
Because
No
in the end
transformation.
you resulted in the same place.
Okay. It ended up with the same energy at the end, right? Okay, it's the same potential energy. Okay, here. Here you go. So let's say I do this. Ready? From now.
Then you'll get tired again.
To now.
No.
No.
Yes.
No work.
No way.
There's no
But I'm sweaty.
because there's no work.
It was saying.
All right. Okay. Now that may have been a lot of work in the in the English language, right?
Yes.
Work. Oh, a lot of effort, right? But that's not work according to physics because the energy of the book hasn't changed, right? Now this is positive work. So what's this?
Negative work.
Negative work, right? Okay. And when I started off, That's positive work, but when I stop, that's negative work. So the net work that's done from beginning to end is 0, right? Okay, very nice. So work, if you think about it in a broad scale, if you're not transferring energy to the object from beginning to end, then there's no net work done. Now, was there work done in the middle? Sure. But there was positive work and negative work done. So overall, there's no work at all, right? No net total work, okay? All right, that is one way to think about work. The other way to think about work is strictly from a mathematical standpoint. And so work equals the change in energy of the system. And this is the work done, external work on it. The other way to think about work is what you learned last year. Work is equal to F. All right, technically it's F dot. Okay, look at our equation sheet. Get out your equation sheet. Yeah, because last year in pre-AP you probably did displacement D. Actually, you probably wrote it last year like this. F D cosine theta. Is that the way you wrote it? Okay, so our equation sheet does like this. F delta R cosine theta. Is that right? That's right. F pointy thing R cosine theta. All right. That means delta. That means change. Okay, so there must be a displacement. That means it has to go from one place to a new place. Now, R means radius. Okay, so that means from the beginning spot radially out to the new spot. Okay? Some books will have this as S. Some books will have this as S. Technically, it looks like this. Work equals F dot R. Okay, dot product. Do you know dot product from math class?
No.
Okay.
Oh, wait, hold on. Is it when you multiply a vector and,
All right.
and a scalar? No.
Vector
No.
times a vector.
Yeah, vector times.
All right, here you go. When you were little bitty kids, you learned 4 times 3 equals 12. Right? And then when you're a little older, you learned 4 times 3 equals 12, right? Okay, now if these are scalars, those mean exactly the same thing. But if they're vectors, they mean two separate things. If I have A cross B, I get vector C, but vector C is going to mathematically be, I'm going to get A, B, sine theta, and this is a vector. A vector answer. Okay? If I do A dot B, vector times vector, then I get A, B, cosine theta, and this is a scalar. All right? So the one we're doing is a dot product where we have a vector, a force. A force is a push or pull that has a direction associated with it. You push something one way or you pull it a different way. And a radius has a direction or a displacement, right? But our answer is going to be F, they write delta R to remind you it must move, F delta R cosine theta. Okay, we'll talk about the theta in just a minute. All right? This is a scalar, which means it's just a number that has a magnitude plus or minus. Okay? And if it's plus work, it's adding energy. If it's minus work, it's taking energy away. All right? Okay, just as a side note, because we're going to run into cross products a little bit later. You ran into cross products last year in magnetism. You may not have known it. Okay? Here's the way this works. Okay? Let's do this. Let's say that vector A is this way, and vector B is this way. All right? Okay, everybody? In order to get the vectors right in cross products, you have to use your right hand. Okay? And you have to look silly. So take your right hand, point your fingers in the direction of the first vector. These fingers, point them in the direction of the first vector. A. Now curl your fingers in the direction of the second vector. So it's A cross B. So it's A, curl your fingers towards B. So point your fingers towards A, curl your fingers towards, wait a minute, B is this way, right? So I'm going to stick my hand like this and curl it this way, right? Now for you it's a little harder because you're looking at the board. It looks like this to you. And guess what? Your thumb points in the direction of the answer vector. So A cross B would equal vector C this way. Now you all did that in magnetism, even though you might not have known that. Do you remember doing right-hand rule? That's what that is. You never learned it? You'll learn it this year. Shh, stop. We have you on tape.
No names were said.
He did.
No, but you don't know mine, so.
That's right, Jennifer.
I think the voice
Beatrice,
Yeah.
whatever your name is.
is missing
I get it now. I think this.
All right. Now, dot product, on the other hand, is just you take the vectors. By the way, cross product, just so that you know, I erased it already, but here's vector A and here's vector B. Cross product, it's very important you have them in the right order. Because if you do A cross B, then your thumb points this way. What if you do B cross A, backwards? B
Okay.
cross A, and your thumb points the other way, right? You'll get the negative of the original answer, the opposite direction. Okay, so cross product is cross product you have to have in the correct order. And mathematically it's A, B, sine theta, and that's the numerical answer, the magnitude. And then the unit, the direction is your thumb. Your thumb point gives you the direction of your answer. Okay? All right, if it's a scalar product, a dot product, you just do AB cosine theta. Now, some of you are wondering, what's this theta? Where do we get this theta? Yeah, the angle between what?
the ground and the
The ground.
well
Some
the surface.
point, any point.
All right, here's the deal. If I have vector A this way, and let's say vector B is this way, all right? The angle, anytime you have a dot product or a cross product, or anytime you see a problem like this, where you have a vector and an angle, okay? Vector, vector, angle. This angle is always the vector between these two, okay? So, here's how you do that. Just take these two vectors and extend them until they cross. They cross right here, okay? And when they cross right there, you take the angle, the smallest angle, between the two vectors. So it's either this angle between the two vectors, or it's this angle between the two vectors. You don't want the big angle, you want the small angle, right? So that's angle theta, right there. Does that make sense? Okay. So some students will think of it this way. They'll think of them like a pair of scissors or whatever. Okay, it's the angle between the scissor points. Okay? All right, now what if you have something like this? What if you've got a vector that looks like this? Here's vector F, and let's say here's vector R. Delta R is this way. Okay? Well, you would just extend them. All right? This one's pointing in this direction. This one's pointing in this direction, so that would be our angle, right? Okay, so what if we have one like this, though? So we have an object, and somebody's pulling it this way, but it's moving this way.
Right there.
Okay, then the angle would be this angle, right? That make sense? Okay. Now, by the way, when I say that it's being pulled this way and moving that way, a lot of times that really messes with students' brains. Okay, how is it possible for something to be moving one way, but you pull it in a different direction?
Pushing.
What's that?
Somebody's pushing it.
It could be that there's another force on it still, right? Or it could be that it's already in motion. Okay, like for instance, somebody's running down the hallway and you're trying to stop them, and so you grab their grab their shirt,
Collar.
or their collar, or their ear, okay? And so they're going that way, but you're pulling them this way, right? Okay, so you're slowing them down.
Or trying to hold on.
I get
to it.
upset because you just stressed out my
Okay?
shirt.
Yeah, or like, for instance, driving a car. You're driving a car, you step on the brakes. If I'm driving my car that way and I step on the brakes, I'm moving that way, but which way is the force? Hopefully that way, because that will slow me down, right? Alright. So we've got a little off topic, but that's okay. You're going to run into dot products and cross products eventually anyway. Alright, so here we go. I have an object like this. Let's say it's moving from here to here, and I apply a force this way. Or that's case A. Here's case B. It's moving this way, but I apply a force this way. Or here's case C. It's moving this way, but I'm applying a force this way. Alright? Well, that's not enough cases yet. So how about if it's moving this way? Here's case D. And I apply a force this way. Or case E. Let's say it's moving this way, and I'm applying a force this way. All right, now. In which cases is the force doing positive work?
A and D.
Okay, now you can think about it right from this equation right here, right? Well, the force is a vector, so it's going to have a value. The distance, in our case, our distance is going to be x instead of r, right? It all depends on that angle, right? Okay, under which cases will I end up with positive work? What does my angle have to be like? Less than 90 degrees, because the cosine of 0 equals 1. The cosine of 90 equals 0. Anything between here and here is going to be positive, right? Anything between 0 and 90 degrees is going to give me a positive number. So if all of these forces are exactly the same, and all the x's are exactly the same, then this one's going to give me what amount of work? The work here is going to be f x cosine theta, but that's going to be just fx, because that is going to be 1. Because the angle between those two vectors is 0. Cosine of 0 is 1. Alright, so if this angle here is theta, then the work done here will be fx cosine theta, but it's going to be positive, isn't it? Okay? And this is going to be positive. I'll just put the positive up there. Alright? Okay, so when am I going to have negative work?
At C.
C
C and
E.
And B's 90. B's exactly 90.
Ah, B, theta equals 90 degrees. Cosine of 90 gives me 0. So the work done here is going to be 0. No work done.
Same for E.
Same for E?
That's 180.
Ah, the angle here is going to be something, it's going to be a large angle, but the angle here is going to be, what, oops, I should put greater than 90 degrees. So therefore the cosine of theta is going to be a negative number. Unless I'm beyond, well, yeah.
Unless you do whatever the
Yeah, we're just talking, we got an angle between 0, okay, hang on, greater than 90 but less than 180. How's that? Does that help you out? Alright. So this is going to be negative work because it's going to be f x cosine theta, but this is larger than 90, less than 180, so I'm going to have a negative amount of work. This one over here is going to be work equals Fx cosine theta, but that's going to be equal to -1. So I'm going to get, my work is going to be negative. It's going to be negative F times x, right? Okay, now, let's think about it in broad terms. Everybody okay with this? That the angle will determine whether, the angle at which the force is relative to the displacement is going to give you whether the work is positive, negative, or zero. So now, remember, work transfers energy. So, this is transferring energy into the object. This is transferring energy into the object. Okay, let me give you an example. Wait a minute. This one's transferring no energy into the object. And these are transferring energy out of the object. Okay, let me give you an example. Okay, so here's a wagon. Okay, the wagon is being pulled by the handle. So there's a pulling force here. What other forces act on the wagon as you pull the thing along? It's going to be gravity, right? It's going to be an mg. What else? It's friction. Which way would friction be? Okay, if it's being pulled to the right, if it's going to displace to the right, then friction will be this way, right? And so what
The
else?
surface holding it up.
Okay, the surface holding it up. What's that force called?
Normal.
The normal force. Very good. So this is the normal force. F sub n, force normal. And really, I always write mg, but you could write F sub g. So all of your forces are an F with a subscript telling you what kind. All right? But I'll write mg a lot. And actually, you can call this one n if you want. And this one you can call, don't just call it F because it'll look like a random force. Sometimes books will write it kind of like a script F for friction. All right? As long as it's something reasonable that designates what it is, you're going to be just fine. Okay? All right, so let's look at each one of these forces. Which of these forces is doing positive work, adding energy to the system? Yeah, this is doing positive work. Is it doing the max amount of positive work?
No.
How could the person pull on the wagon and get more work into it? Yeah, because some of this pulling force is trying to lift the wagon off the ground, right? If they would just pull it horizontal directly, they would add more energy to the wagon. Does that make sense? Okay, so you're doing positive work here, but not the maximum you could be doing. All right, so what's friction doing? Negative work. It's taking energy away. In fact, think about it. If you're in a car and driving along and you take your foot off the gas, friction certainly does negative work on the car, right? Car's going forward, the friction is doing negative work, slowing your car down, taking the kinetic energy away, right? So this is doing negative work. Hey! Well, hang on, I'll ask that question in a second. What's that and that doing?
Negative.
There are several things. What's it doing?
Balancing it, keeping it on the ground.
Balancing it and keeping it from falling through the ground or being shot into the air. Okay? It's also doing what?
Negative one.
No work.
Ooh, negative work or no work?
Negative on the
Neutral.
here.
No, because it's 9 degrees.
Why no work?
80.
It's moving
it balances it
horizontal.
out.
Because the angle here is 90 degrees.
Oh, right direction.
And the angle here is 180 degrees. And the angle here is less than 90 degrees. So we got positive work, negative work, and the work from these is 0. Now I will caution you, for those of you who are saying that this force and this force are canceling each other out. Don't forget, we have vectors here, right? So does this one and this one have to be equal?
No.
Or will they be
No,
equal?
no.
No. Because we have part of this force pulling up, right? So this up force here and this up force here will cancel this down force here. Does that make sense? Okay, and hey, by the way, look. Do you see how this pull force, some of its force is wasted? Because some of this force, the up part of the force, is doing no work, right? But the horizontal part of the force is doing all the work, right? Does that make sense?
Yes.
Okay. Is it possible for there to be no net total work going on here?
Yes. If the guy's too weak to pull it anywhere.
okay, if this force isn't enough to overcome that, or you could say, well, if this positive work equals this negative work, then there would be no net work. And so what would that look like?
You pulling on the wagon and going nowhere.
That would look like this, or it would look like this, moving at a constant speed, right?
Oh, yeah.
So it's possible that the kid could be pulling this wagon across the ground at a constant speed, and if it's moving at a constant speed, there's no change in kinetic energy, so therefore no work done. Does that make sense? Okay. So it's possible that even though there's one force doing positive work, there could be other forces doing negative work, so the net total work would still be zero, right? Just like when I was walking that book across the room, right? Okay. So adding energy, taking energy away, not doing anything as far as energy is concerned, right? Okay. Excellent. Excellent, excellent, excellent. So there are a couple of ways for you to think about how work is done. Okay, you can think of work strictly in this sense, the equation sense, force, displacement, and the angle in between them. Or you can think of work in a more global sense of, well, has the energy changed? Like for instance, let me give you an example. What if you're here and you've got to climb all of these steps and you end up here? And what if I gave you the angle? I gave you that you move this, here, I'm going to make things really bad for you. I'll do this. How about I say that this angle here is 30 degrees, and I'll say that this height here is 10 meters. You're going up a large flight of steps, okay? So 30 meters is about 30 feet, so that'd be like going from first floor to third floor here, right? And let's say that you have a mass of, 70 kilograms, all right? And I say, well, how much work do you do by climbing those steps? And you go, oh, no. Because I got to solve it this way, right? I got to figure out how far I went, which is this. That's my delta R. And then I got to figure out what force is required to take me up these steps, right?
Just use the 10 meters. Get potential energy at the end.
Hey, okay. This is a hard way to solve it in this case, right? Or you could do, hey, work changes the energy of the system, right? What kind of energy am I changing? Potential energy. So I could say, well, the work is equal to how much my gravitational potential energy is changing. Assuming I start from rest and end at rest. Or if I climb them at a constant speed, right? No kinetic energy changing, right? So that's just going to be mgh final minus mgh initial. Or it's just mg delta h, right? So 70 times g, which is 9.8, right? Times the height, which is 10, and you're done. So keep an open mind when you're thinking about work. A lot of times, just figuring out what kind of energy is changing is the easiest way to figure out if there's work or not. Okay? Let's talk about orbits. So here's our sun. And here's the Earth going around the sun. Okay, as the Earth transfers from here to here, how much work does the sun do? None. The work is hot. The sun is hot. It's sweaty. It must be work. Yeah. Why none?
There's no radius does change.
But it's moving. There has to be displacement.
Well, we're assuming this is a perfect circular orbit.
Okay, well, if we assume it to be a perfectly circular orbit,
Then there's no
radial.
there's no radial displacement. So what? I don't care.
Well, when you put it into the equation, that's what
Oh. So work equals F delta R cosine theta. Hey, there's no delta R change, right? So it's the same? Here's another reason why. Which way is it displacing? That direction. Which way is the force? That direction.
90 degrees.
Ooh, 90 degrees. 0, zip, no work. Anything going in circular motion at a constant speed, then the force that's causing it to go in the circle, the centripetal force, very good, doesn't do any work. Okay? Now let's look at a different type of orbit. What if we have an orbit that looks like this instead? I should have just left it. There we go. What if we have an orbit that looks like this, and so the orbit is elliptical, like an asteroid or like a comet? So the Earth or the comet is right here, and it moves from here to here.
There's a change in radius.
All right, now there's a change in radius now. Which way's the force on the comet right here? Towards the sun, right? And which way is it displacing? It's displacing in that direction, right?
It's less than 90.
Ooh, angle less than 90. So positive or negative work?
Positive.
Now wait a minute. If there's positive work done, what's happening to the comet? It's going faster and faster. Because if you think about it, what kind of energy does the comet have? Well, the comet has kinetic and it has gravitational potential. This kind of gravitational potential. So it has 1/2 mv squared, but it also has this, technically it's negative, negative g m1 m2 over r squared, right? Oh, I did it again, sorry. Dang it. That's r. Hey, you don't know me well enough to say it's terrible yet. Wait till next week. All right, so yeah, that was terrible. So there's our energy, all right? And as you go around, this radius is getting smaller and smaller, right? Okay, now this is really weird, but as the radius gets smaller, what happens to this number? It gets larger, but it's a larger negative number, which means it makes the total energy of the system get smaller. Now, let me say that again, because that's kind of confusing. If this radius gets smaller, then this number gets bigger, but it's a bigger negative number, right? So that means that the total energy of the system is getting more negative, right, or smaller. So its radius is getting smaller. Uh-oh, did I just fly into the air?
Tighten it.
No, you actually sunk into the ground.
That's right. I'm gone. All right. So as the radius gets smaller, the potential energy is getting smaller, taking this energy downward, right? That means that there's positive work being done, right? And if there's positive work being done, but this thing is taking the total energy down, that means that this must be getting much bigger, right? Does that make sense? So, it is correct. When the planet goes this way, you have positive work being done, and the positive work is going into making this comet go faster and faster and faster. Think about it for a second. Y'all, well, shoot, you're of the wrong age to know Halley's Comet, really. All right? So, Halley's Comet will come back in your lifetimes, 80, 40, about another, see, it came back in 86. It has an orbit of around 80, so it's going to come back in when? 46? 2000?
Wait, when did it come?
8, 9, 10, no, 2066. So, how old will you be?
Like 70.
70.
Oh my god.
Oh, I don't want to be that old. Yes, you do. You want to be that old, because the alternative is not good. You want to be that old. Be proud to be old, okay? All right, so when you're in your 70s, 70s approaching 80, Halley's Comet will come back. Now it takes 80 years for Halley's Comet to go all the way around. But how long does Halley's Comet stay in our solar system where we can see it?
Not that long.
Not that long. Months. Why only months? Because it is cruising fast over here. It's going really fast as it goes around the sun. And then when it gets over here, what does the sun do to it? Slows it down by doing what kind of work?
Negative.
Negative work. And so while from here to here it takes months, from here to here it takes 60 years. To go out there and go really slow. And come back. Right? And then slowly speed up. Okay? So, in an elliptical orbit, you have positive work being done on the way in and negative work on the orbit when you go back out. But wait a minute. But wait, there's more. What if you started here and you go all the way around and end up back here? How much work was done? None. Because assuming you end up back at the same place, at the same velocity, then the total net work being done will be zero. Okay? So when they talk about work, you got to be careful. You got to know the beginning and ending conditions. And that will tell you whether there's positive work done or negative work done. Because, like for instance, when I was saying, okay, not now, but now to now, right? It makes a difference on where you're beginning and where you're ending as to how you're calculating your work. Does that make sense? Okay? So you need to know your starting spot and your ending spot. Okay? All right. Let's also talk about work done by a force that's not constant. Okay? Because I told you that work is really this, I lied to you. I hope you know that physics is the study. When we teach you physics, we lie to you less and less as time goes by. Because we say, oh, don't worry about friction. Oh, don't worry about that string having mass. Or that thing, we'll say, there'll be fancy words like, there in this problem there will be, it'll be frictionless surface, and this pulley has no mass. It's a massless, frictionless pulley, and you'll have an inextensible string. That's a fancy word for it. It's not stretchy. Can't extend it. And they'll have all these fancy words because they're making it simple at the beginning. What would the world be like under these conditions? And then they say, okay, but we'll add a little bit more on here. Let's add friction. And then we add drag. And then we add other things, okay? Those of you, you'll take Physics C next year, we'll add more and more stuff in to make it more like what the world is really like, okay? So, here's what the world is really like for work. It's the integral of f dot dr. For those of you that have had calculus.
The change in the...
So it's force dot dr. Now, what does integral mean? Very good. The physical meaning of integral is that it's the area of a graph. Now, we do not need calculus in this class. However, it comes in handy that you know that calculus, the integral, means the area of a graph. Okay, that's all you need to know is the area of a graph. Okay, so here we go. All right, for all you calculus people then, work equals integral f dot dr. That means it's going to be the area of what graph? The force versus radius or displacement. Any one of these dimensions, x, y, could be height even. Okay, anything that's in units of meters here, this is in units of newtons. Okay? So what you end up with, I'm just going to put x here to make life simple. X. Alright? So the deal is if the force is constant, okay, so work equals F delta R cosine theta. If we assume the force to be constant or an average, then say the force was 10 newtons and you moved it 10 meters. And let's say here it is. You moved it 10 meters with a force of 10 newtons. Well, the work then is going to be 100 what? Newton meters. Okay, let's go back. What's a newton again?
It
F
is
equals MA.
1 kilogram.
That's a Newton, and this is a kilogram
times 6
meter per second squared. So a Newton is a kilogram meter per second squared, right? Okay. A Newton meter is a kilogram meter per second squared times a meter, right? Which gives you a kilogram meter squared per second squared, which happens to be a joule. All right? So this will be in units of joules. 100 joules. All right? So if this force is 10 newtons and we move it 10 meters, our area is 100 what?
joules.
Joules. 10 times 10. 10 newtons times 10 meters is 100 joules. All right. So what if we have something that's a non-constant force? Like our spring. The force from a spring, remember, is Kx. Now I'm going to neglect our negative sign here for a second because I'm going to avoid making the math any harder than it needs to be. So if this is the force from my spring and this is the displacement, then what's this graph going to look like? Well, you math people.
Oh, it's going to be...
Y equals mx plus v. That's on my y-axis. X, coincidentally, is on my x-axis. What's my y-intercept? 0. And what's my slope?
Okay.
That's a linear line, isn't it? As opposed to a curved line. And so it's going to look like this, or should look like this. This is the force in a spring, depending on how far you stretch it. And the slope equals K. So what are the units of K? K is literally the slope, which is rise over the run, which means change in force over change in displacement. So it will be in units of newtons per meter, right? Newtons per meter. Right? So your spring constant is in units of newtons per meter, and this is in meters, and so that turns out to be newtons, right? So newton per meter times a meter gives you a newton. All right. So a little sidestep here. Get our forces in. But wait.
There's no...
So let's say here's your mass. And here's your spring. All right? And let's say that I take this mass and I pull it all the way out here. Say this is its equilibrium position, which you talked about, right? And I move it all the way out here to X. All right? So it begins right here, and I move it all the way out here to X. How much work did I do? Well, the problem is work equals, oops, I'm writing the wrong equation. Work equals F delta R cosine theta. Okay, well, how far did I move it? Well, I moved it X. And what's my cosine theta? Well, I'm moving it this way, and that means, and I'm also pulling it that direction, right? Or pushing it in that direction. Either way, right? So I'm either pulling it or pushing it this way, right? So that should be cosine of 0, which is 1, right? But what's my force that I put in there? Do I put the force that's here, or do I put the force that's here? And the answer is, uh-oh, I've got a problem. Because this is a non-constant force, right? All right. It's a non-constant force. So either you have to use the average force average, or you have to remember that work equals the area of the Fx or Fr or Fs, whatever this dimension is here, graph. So how do I find that area? Well, I go right here.
Triangle, basically.
Yeah, it's a triangle. So if you're in calculus, you take the integral, right? If you're not in calculus, then you just find the area of this graph. Okay, so if I find that, then what's that area? The area equals 1/2 base times height, which is 1/2 x times the height, which is the force from a spring. Well, what's the force from a spring?
At the top.
It's k times x, right? So it equals 1/2 x times kx. So what do you get? You get 1/2 kx squared. Whoa, wait a minute. Does that look familiar? No.
KX
Spring
squared.
energy. It's
Energy of
It's
That's spring potential energy. Ooh, think about it for a second. What do you do when you do work on an object? You change its energy. When we stretch the spring, what kind of energy are we changing?
We change the potential.
We're changing spring potential energy, right? So shouldn't it make sense that when we do work with a spring, either stretching or compressing, it doesn't matter actually. And by the way, if I did this technically with the negative sign here, our graph would be like this. The negatives would cancel out. We get the same answer. Okay, I just avoided the negative. It should make sense that if we do work with a spring, either stretching it or compressing it, that we would give it spring potential energy, and that equation for work we end up with should equal the potential energy equation, right? Does that make sense? Just like when we climb steps, the amount of work we do is equal to the change in potential energy over here, right? Gravitational potential energy. All right. So, what if we have a graph that looks like this? Actually, here. Get out your review packet. Okay? And I want you to go to page 3. Page 3 will look like this. Okay, everybody? And go down to the bottom of that page, problem 971. Problem 971. Okay? You have a 0.2 kilogram object moving along a straight line. A net force acting on the object varies with the object's displacement as shown in the graph above, or actually to the left. The object starts from rest with a displacement of 0 and a time 0. Okay? And it's displaced a total of 20 meters. Determine the following. How much work is done in the first 12 meters? Okay, so here's the graph. The graph looks like this.
No, 48.
It's 12 meters.
That's just 48.
Oh, that's 4 newtons.
It's 8. It's 32.
Yeah.
So 20 and, oops, not, and 12 we're interested in. So go across here, and then to here. Okay, so there's our graph. It looks like that, or something similar to that. Okay, what's the work done? Part A. Oh, I'm sorry. The object, the mass of the object is 0.2 kilograms, and it starts at rest at position 0, right? So at time 0, it's at rest, and it's at position 0. Okay? So 0, 0. All right. How much work is done in the first 12 meters? Well, you could do this. Work equals F delta R cosine theta. And you could say, well, the force is what? 4 newtons? And the displacement is 12 meters. What about the cosine theta? Yeah, they don't give us any information about an angle, do they? So we're going to have to assume that that is going to be 1, right? And so then we get 48, what? Joules. Okay, or you could have done this. How else could you have thought about it? You could have thought about it as an integral or the area. And the area there is 48 joules. Base times height is 48. Okay? Okay, part B says, what's the speed of the object then? After 12 meters. Okay, when it gets to 12 meters, what's the speed of the object? So what's the velocity when it gets to 12 meters? How are we going to do that?
You get the kinetic energy.
Well, how can we get kinetic energy? How do you know?
It should be the same as the other.
Okay? Because work was done, right? It's positive work. What kind of energy is that work giving the object? Does it say anything about springs?
No, we have
Does it say anything about gravity, moving up or down?
We don't know, but it is some energy. So.
But we know it's something, and we know that it's starting from rest, and now it's not at rest, right? So that implies that what kind of energy is it being given? Okay, so this should be equal to the kinetic energy it's given, right? The change in kinetic energy. Okay, the question is that's how much it changes the energy, assuming it's kinetic. That's kinetic final minus kinetic initial. Do we know either of those two?
Not yet.
Yeah, we do.
You have to calculate. The initial is 0.
Why is the initial 0?
Because
It starts off with a kinetic energy of 0. So therefore, this 48 joules all goes into giving it kinetic energy at the end, right? Which is 1/2 mv squared. And we know m to be 0.2. So we get 1/2 0.2 kilograms v squared, and that equals, what do we say, 48 joules, right? So we can find our velocity after 12 meters, right? So 48 times 2 divided by 0.2 square rooted. Whatever that turns out to be.
22 meters per second.
Approximately 22 meters per second. Excellent. Okay? The next question is part C. It says, what's the final speed of the object after 20 meters? Now, by the way, we haven't covered forces and acceleration and kinematics yet, but could we have solved this with forces and acceleration and kinematics?
Yes.
Yeah.
Sure, because this force and that mass would give us the acceleration of the object, right? And once we know the acceleration, we could have solved it with some kinematics equations. And it would have worked fine. We would have got the same answer. All right? But now part C, it says, what's the velocity at 20 meters? Okay, now, how do we do that?
You find a total,
Still get the
Say it again.
area.
Well, you need
Okay,
to
what
find
we
the
could do is, we could find the total work from 0 to 20 meters. And that will equal the change in kinetic energy, which is all final kinetic energy, right? You could do the total area. Now that will work. Another way you could do it is you could say, wait, could I just find the work from 12 to 20 meters? Won't that still be the change in kinetic energy? But that's kinetic final minus kinetic initial. This will be the kinetic energy at 20 meters, but what will this kinetic energy be at? Yeah, very good. That'll be at 12 meters, right? So you could solve it that way and just find this little triangle area and add that kinetic energy onto your kinetic energy here, right? Or you could just do it from beginning to end. Either way, you get the exact same answer. Okay, I'm going to do it from beginning to end. I find that easier for me. I prefer to have my initial kinetic energy be 0, but it doesn't matter. Okay, we got to find this area. All right, so that area is 1/2 base, which is 8, times a height of 4 So it looks like 16 more joules. So 16 plus 48 is what, 64? So our total work is 64 joules. And that's going to equal 1/2 0.2 times our velocity at 20 squared. Sorry, I'm running out of room here. Excuse me. Now then the rest is just math, right? What do we get?
25 meters per second.
About 25 meters per second. Now wait a minute. Let's do what you call in engineering an idiot check. Okay? An idiot check is when you look at your answer and see if you've done something idiotic or not. Okay? All right. Does this make sense?
Yes.
Why does it seem to make sense?
Because it's faster since you add it.
Because we've got more work, so it should be faster than this. Okay? And if I had to come up with 53 instead, would that seem reasonable?
No,
Why not?
because that work done is less than the other work done.
Because this little bit of work added on is not, it's smaller than this, right? So you wouldn't expect your speed to double, right? You expect it to be bigger, but not a tremendous amount bigger. So it appears to make sense. So if we don't know the answer, like we're in the middle of a test, and you don't have the key sitting there, and you don't want to look at your neighbor's answer because you know that they're not as bright as you, right?
Well, if we don't know it's on a test, that was
Oh, then that appears to make sense. Now, let's look at this in a big picture now, okay? Work changes the energy of the system. External work, okay? If that work, and that could be any kind of work, okay? So like for instance, how about we have a, here you go. We have a skier going down a slope.
it's like a cloud.
Like clown feet? Here. There you go. Ski pole.
Yeah, it's supposed to have a second ski if it's supposed to have more, relatively to a second floor.
We'll make it as clown-like as possible.
Forgot the hair.
Man, I don't like clowns.
Alright, so there we go. We have a clown skier. The clown is skiing on trick skis, otherwise known as its very large feet.
Oh Lord, what did
Alright.
Looks like a woman.
Picasso, man, that's what that is.
That's a Picasso. Yeah, I'll sell it. Cut it out of the board. Alright. Now, let's say that the clown has a mass of 100 kilograms.
He's fat.
No kidding.
He
He's
doesn't
fat.
look too
Just-
fat, but apparently
It's all that,
Not
bro.
It's all that makeup and
wearing a medley.
fake hair.
Yeah, those feet.
Let's say the distance from here to here is 1,000 meters. 1 kilometer. So it's a long, shallow bunny hill. That if you ski, that's what it's called. It's a bunny hill. That's very shallow. All right. Now, hang on. Let me do a little math here, man. Since I'm making the problem up.
Like a name.
Got it. Let's say that there's friction backwards of 100 newtons. Okay? So let's say that the clown's big feet aren't that slippery, and so there's 100 newtons of friction backwards, okay? So I want to know, when the clown slides down the hill, how fast will the clown be going when the clown gets to the bottom? Assuming the clown doesn't fall. Or stop. Okay? All right. Let's think of it in terms of work and change in energy. All right, since this is friction, force friction, there's an outside force doing work on the clown, right? Which is friction. There's actually other forces on the clown. What are the other forces on the clown? Gravity, force gravity, and there's the normal force, right? Now, assuming no air resistance. We'll neglect air resistance all year long. So you might as well just stop saying that unless we give you some reason to say air resistance.
Ignore it.
Ignore it. Occasionally they'll say something about air resistance, but for the most part we'll ignore it all year long because the math is too hard. All right. Now wait a minute. Is everybody okay with saying the fact that, remember from last year, that this normal force and this part of the gravity force have to cancel? Because if they don't, if the gravity force is larger than the normal force, what happens to the clown? He falls through the mountain, right? What if the normal force is greater than the gravity force?
He floats into the sky.
He gets shot off the ground into the sky. So when you ski, normally that doesn't happen. So we will say the normal force and this part of the gravity force are equal, right? Okay, so we have this part of gravity right here pulling the person down. Now does everybody see that that part of gravity is doing positive work?
Yeah.
And that friction is doing negative work. Now, there are two ways that we can handle gravity. We can either think of gravity in terms of the work that it does, because it's a conservative force. Because it's a force. But since it is a conservative force, we could also consider gravity in terms of what else? Instead of the work it does. We could consider it in terms of its energy that it supplies, right? Because it's a conservative force. So would you rather do this problem in terms of gravity in terms of its work that it does, or gravity in terms of the energy, potential energy it supplies? We can do it either way.
Faster way.
Faster way is potential energy.
Yep.
Okay? Potential energy. And I'll show you that it's going to turn out to be exactly the same either way. It won't make any difference. Now, can we take care of friction in terms of its potential energy? Yeah, exactly. What? Is friction a conservative force? No. So is there a frictional potential energy? No. So can we handle this in terms of energy alone? There is no such thing as potential energy for friction, right? So we have to take care of it in terms of the work that it does. That's our only option. Okay? So here you go. So, work is being done by, we're only considering our non-conservative forces. Work done by our non-conservative forces is going to equal the change in energy of the system. Okay? So that's going to be F delta R cosine theta equals the change in energy of the system. Well, what kind of energy is going to be changing? What kind of energy is involved here? What kind? Gravitational potential and kinetic. So we're going to have the energy, let's do it one step at a time. Energy final, or 2, minus energy 1. Would you prefer me to use F for final and I for initial? Or is 2 and 1 okay? Doesn't matter. 2 and 1's okay? 1 comes before 2, so 2 is the final and 1 is the initial. Okay? Alright. So what kind of energy is it that we start with? So we're going to start with gravitational potential. Is the clown moving to start? Let's say no. Let's say the clown's at rest. What kind of energy does the clown end with? Kinetic. Why do you say kinetic and no gravitational potential?
It'll be at the bottom.
Oh, because it'll be at the bottom and we call that height equals 0? So if we call this height equals 0, then the clown will be moving 1/2 mv squared, but the clown will not be above the ground anymore, right? It won't be above 0. So this is my final energy, all kinetic, and my initial energy is all potential. Is that okay? All right. And that's going to equal F delta R cosine theta. Now I'm going to go up over here because I'm out of room. Okay, what's my force? That's friction, right? And that friction was 100 newtons. What's my delta R? 1,000 meters. What's my cosine theta? Ooh, very good. -1. Why -1? Because friction's that way and you're moving that way. Cosine of 180 is -1. If you had forgotten the -1, you would be accidentally having friction add energy to the system. Now that can happen, but not in this case. All right. What's our final kinetic energy? It's 1/2 mass of 100, and that's my velocity at the bottom squared, right? Minus the mass of the clown times g, which is 9.8 meters per second squared, and height. What's the height of the clown?
We find that using.
Oh, we got to use a little bit of trig, right? This is the height. Hey, if you remember your special triangles,
It's well,
are a 30, 60, 90 triangle. If the short side is x, the hypotenuse is 2x, and the long side is x square root of 3, right? Okay, so
that's 500.
the hypotenuse is 1,000, and this is the short side, right? So that should be 500, right? All right, so tell me, how fast is the clown going at the bottom?
Wait, is it the height?
What's that?
How was supposed to do the height?
So this is, what, 100,000, and then I get 50 v squared minus, I have to do that one. Oh, where's my calculator?
490,000.
490,000?
Oh my god.
All right, so I move things around. I end up with 50 v squared equals 390,000, right?
No, 480,000.
480,000?
No,
It's because
it's
it's
both.
10,000.
Both of them are negative, so
Yeah.
Yeah, I'm going to add this to the other side.
It's not
Oh,
3, it's
yeah.
5.
Yeah. And so what's v at the bottom?
V equals the square of.
Square root of
Is a square root of.
That divided by 50.
390,000 divided by 50.
So you can chop off the 0, so it's 39,000 divided by
3.
Oh, that makes it simpler.
I know.
5. No, but it's an even number, 5. Right? And it's a 390.
I get 88 meters per second.
It's a perfect square. Is that really a perfect square?
No.
Yeah.
It's 88.3.
Oh, yeah.
All right. So approximately 88 meters per second. Hey, by the way, everybody, 88 meters per second. That's fast. That's 45 meters per second. It's like 100 miles an hour.
Oh my god.
That is one fast-moving clown. Hey, by the way, if any of you have skied, that's why you don't do this, right? and just point them straight down.
I do that.
Not as bad as Johnny.
Now, why won't, even if we point our skis straight down, why won't we get 88 miles an hour? Yeah, because we will end up going fast enough that air resistance makes a difference, right? Now, we've neglected air resistance. That cloud's not going to get that fast. All right? All right.
What was you?
Okay. Everybody okay with this? Work equals the change in energy. Now, everybody, what if we had thought what if we forgot about gravitational potential energy and we solved it strictly in terms of work? Okay? And so we did this. Work done by all forces equals the change in energy of the system. Okay? What are my forces this time? Well, I'm going to have an F delta R cosine theta for friction.
It says 4 cosine.
That's a delta.
And if I have F delta R cosine theta for gravity
Gravity.
equals, what kind of energy will be changed then?
Again.
If we take care of gravity here, then the only kind of energy that we'll have over here will just be kinetic, right? Okay, this is called the work kinetic energy theorem. If you take into account all types of forces, no matter if they're conservative or non-conservative, then the only type of energy left over here will just be kinetic energy. So you'll have kinetic energy final minus kinetic energy initial, and the initial for us was 0. Okay, do you see that this side over here is going to be exactly the same as it was up there? You're going to get negative 100,000. Okay? But what about our gravity number here? Our gravity number is going to be the force of gravity. Right? It's going to be the force of gravity. What's the force of gravity on this clown? It's going to be mg, right?
980.
For the clown, it'll be 980 newtons. What's the distance the clown's going to travel? That's delta r, which is going to be 1,000, right? And what's the cosine theta in between the clown?
Again.
I mean, in between the force and the direction they're going.
60.
Ooh, does everybody see that it's not 30? It's this and this, right? There's my theta for that. That's 60, right? Anybody? What's the cosine of 60?
1/2. It's 1/2.
It's 1/2.
If you 1/2.
Good job, Melanie.
So wait a minute. What's 980 times 1,000 times 1/2?
980 times 100.
980 times 500.
So 98,000. Oh.
Isn't it 490,000?
Yeah.
And won't this be a positive 490,000? And won't that be a negative 100,000? And won't I get the exact same answer?
Yes.
Yeah. Exactly the same answer. Okay? So, you can decide how to solve it, but I think for most students it's easier, instead of having to figure out the work done by gravity, to consider its potential energy instead. Now, let me make this really clear, everybody. When you're talking about conservative forces, springs, electric, gravitational, and you're doing a problem like this, where work equals the change in energy of the system, you can either think of those forces in terms of the work they do, or in terms of the energy they provide, but not both, because then you'd be double dipping, right? You can only do one or the other. And for most of you, it's probably easiest for you to think of the work done by non-conservative forces equals the change in energy of all the different types of energy we've done. So gravity and spring and electric you won't put over here, you'll put them over here instead. Does that make sense? Okay. All right, well, let's say there was no friction. Let's say that the clown got special clown shoes. And if there is no friction, then how does the problem change?
You take away the
Take off the
first-
negative 100,000.
Yeah, you take off the work done by the non-conservative force. And if you take off the work done by the non-conservative force, all of that, then this negative 100,000 goes away. But wait, we already know how to do that. Look, if the work done by non-conservative forces, non-conservative force, equals 0, that means that the change in energy of the system is 0. That means energy 2 minus energy 1 equals 0, which means energy 1 equals energy 2, and what do we call that? Not equilibrium. Conservation of
energy.
energy. All right. If there's no net non-conservative forces, so if the non-conservative forces add up to 0 or are canceled out, or they don't exist, then the energy of the system won't change. And we have conservation of energy. And so then we would just say that the potential energy of the clown will convert into kinetic energy of the clown as the clown gets to the bottom, right? Excellent. Now, which would you rather solve? Problems where there's friction in them, or problems where there's no friction and you have conservation of energy? No friction's much easier, right?
So that's all it's
It's not easy, it's just longer.
No, but thank you for participating. All right. Now, there will be problems on the test where we'll say, assume no friction, right? And then the energy before will equal energy after. But if there is friction, then you have to take it into account, right? And you can either say, look, that the friction is taking some of the energy away, and so the velocity at the bottom, or the kinetic energy at the bottom, is not as great as it would have been. Okay? And where is that friction force taking the energy away? What's it turned into? It's turned into thermal energy, right? It does. It melts the snow, literally.
You know that, right?
Okay, on that same page that we were just on, you've got this crazy looking thing. Okay? This one right here. All right, I want you to solve that problem on the top. It says there's a track on a frictionless arc x to y, which is quarter circle of radius r. And it has a rough section from Y to Z. Block A of mass M is released from point X and slides down the curve. It comes to rest at point P, which is a distance L away from point Y. Oh my goodness, all these letters. Express your answers in terms of M, L, R, and G.
Why did it come to stop at point? Wait, there's no.
Okay, good question.
Well, no, because the total kinetic energy is nothing.
Yeah, very good. What happens is that the curved section of the track is frictionless, but the horizontal flat section of the track has friction. Okay? I'll draw a picture of it up here. I'd like for you to work this quick. Check your answers with your neighbor, and I will write it up on the board so everybody can see it.
Yes, sir. Okay.
There's friction on mine.
This is an old problem. Some of the newer problems, they'll draw like a rough surface here, so you kind of have an idea that it's rough here, but frictionless here.
Okay, from Y to P, calculate change in.
Okay, so it starts here from rest, slides down to here, and they want to know what's the velocity here at point Y. and then it comes over here at point P and it stops. Okay? So they want to know A, what's the velocity at point Y? B, what's the thermal energy generated? Going from Y to point P. And then C, write an expression for the frictional force. So frictional force equals what? Okay? So let's handle it one part at a time. From X to Y. Okay, anytime an object is changing in height or changing direction as it moves, good bet is conservation of energy if possible. Is it frictionless? Yes. Do we have the same energy here as here? Yes. So for part A, the energy at point X will equal the energy at point Y. What kind of energy do we begin with at point X? Gravitational potential. What kind of energy do we end up with at point Y? Kinetic. Our gravitational potential energy here is 0 because it's on the ground. Height equals 0. Our kinetic on this side is 0 because it's not moving. Okay, so we get mgh. Oh, I already have it written up there. So what can I do? I can cancel out my m's. So my velocity is going to equal 2gh square root, right? Can I use h in my problem? No, I don't have an h. So what is h? That's 2gr. Okay, we're going to finish this problem up next time. Remind me that we need to finish this problem.